it out. And let's just make sure we can actually read what's on the. There we go.
So,
All right.
okay, I'm gonna ask an embarrassing question. How many students are here? 3.
Today is the last day of classes, so there is stuff due
okay.
at 11:59 today that I'm sure people are working on.
Yeah, that's why we have recording. But
Okay, well, that's too bad. Anyway, so this is part 2. I guess it's been 2 months or thereabouts since part 1. In between, I had a hernia operation, which went fine. So I am a little bit more comfortable, although it wasn't really bothering me before. So anyway, this is part 2. And in part 1, I put up some conclusions, and that is that, hey, ham radio operators have got lots and lots and lots of spectrum space above 1 gigahertz as compared to below 1 gigahertz. That's not a big surprise, but it's a shame to just see it there and not use it. Using those bands can be a bit challenging, but it's remarkable how much stuff you can find at flea markets and all kinds of junk places to make your life a whole lot easier. And there's a fair amount of commercial stuff out there now too. So it can be challenging, but it's great fun. So there you go. You too can make a microwave station. Among other things, out of a police radar. Because guess what a police radar is?
a microwave radio.
It's a microwave transmitter and receiver. It's what's called a homodyne receiver. That means it mixes the outgoing signal with the return signal, and it's looking for the difference in those 2 signals, and that's proportional to your speed. So if you know the RF frequency, and if you know the audio pitch between those 2 signals, guess what? You know the speed. And put some software after that, and lo and behold, you have a speed meter. But you can make use of that same kind of homodyne thing to do real communications too. So anyway, let's get started. So what might be equipment building blocks? Well, signal sources, your transmitter. You have to have something to make RF to send it someplace. Raw signal sources makes a signal. How do you make a signal? Oscillators, synthesizers, which is a very, shall we say, a controlled oscillator. And you need to have something to refer that synthesizer to, so you need some kind of a frequency reference. It might be an expensive one, or it might be a relatively inexpensive one. You can get some pretty nice small references these days that are pretty darn good. Over here, I will pass around a couple of reference oscillators. One is medium size. They make them about a quarter of that size that are still pretty good. And then a very large one. And the very large one is neat because it's got a very substantial amount of thermal isolation. And that means it doesn't use much power. Both of those reference oscillators have a pin on them, which allow you to change the frequency a little tiny bit with a voltage. So that allows you to take that reference oscillator and then control it from a GPS receiver so that, lo and behold, you can lock it to GPS if you really want to. Turns out that those reference oscillators are really pretty good, and for any of the modulations that hams use now, even at 10 gigahertz, they're good enough standalone. And that's nice because it means that you can go driving around the countryside and you don't have to have a GPS signal to keep it happy. Anyway, frequency converters. They move the signal up or down in a more or less linear fashion. Or you might use a multiplier, which is not linear. And multipliers are very handy, even if you don't think you need I'll show you what. Somehow, you've got to have a reference that is usable by your equipment. And if no other reason, synthesizers can be used to create a signal at a high frequency using a reference that's very low. Like at 10 megahertz, you might have a reference. You might want to make a signal at 10,244 megahertz. Synthesizers can do that, but you do have to have reference. So to get frequencies at some other frequency than wherever like where WWV is or where your standard reference is, you need some way of moving things around. And then modulators to impress the information onto your carrier frequency or onto the signal that you're sending out. And there's all kinds of modulation. The simplest one is, I'm going to turn this thing on, I'm going to turn it off. Okay, that may be of some value. If you turn it on and off in some kind of code, Morse code might work. Lo and behold, you can in fact send information very simply that way, just turn the darn thing on and off. Now, there can be some issues, because if you turn something off completely and then turn it on, its frequency is going to kind of go meow in a screwy kind of way until it gets to the standard frequency where it wants to live. So it's easier to turn off an intermediate stage to turn the signal on. Then you can have AM, which is a more elegant way to turn things on and off. FM, change the frequency in relationship to the information you're trying to send. Phase modulation, and all manner of variations on a theme digitally. Signal detectors. No, directors. Sorry about that. Guess what? Antennas. You got to somehow move the signal into the ether. You don't have an ether, but you know what I'm talking about. Got to get it radiated, and you got to receive it. So in the microwave region, yes, you can use a dipole. We can use Yagis, at least at the lower microwave frequencies. Loop Yagis at moderate microwave frequencies still work. And then parabolic dishes, horns, and lenses are all in the game. And yes, they really are microwave lenses. Then there's a slot antenna, and there are patch antennas. Somewhere over here. Yeah, there it is. Lo and behold, patch antenna for 2.3 gigahertz and 2.4 gigahertz. That's that, or maybe you can read what it says for gain. 19 dBi. 19 dBi gain, so not too shabby. So what's a patch antenna? Well, we'll get to it in a little while. Basically, it's a it's a patch of copper on a printed circuit board, and that patch is resonant at the frequency that you're trying to transmit or receive. And so it works like an antenna element. Okay, now, one interesting thing about antennas is that there's almost always somebody else who comes up with another way of building an antenna. It never, ever stops. When you think it stopped, somebody else will come up with a screwy idea, and maybe it works and maybe it doesn't. But it's a very interesting situation. There's always a new way. And then signal filters. Well, what for? To select desired signals and reject noise and reject undesired signals. And sometimes to do that inside of the radio set too. Signal receivers. Raw detection of a signal at a transmit frequency is the simplest possible way to build a signal receiver. What do you mean by that? Well, the first and most obvious one is a sailor watching a blinking light being turned on and off by a sailor on another ship. That's not a radio system, or is it? Well, it's not radio in the conventional sense, but it is an electromagnetic wave. That light that's being turned on and off on the other end is indeed an electromagnetic wave. So I guess we could argue, yeah, that's a simple transmitter. Okay, now direct detection of a laser with a diode after a lens. Gee, now that's beginning to look like a real system. You actually have a receiving antenna of some kind, the lens. You're focusing that onto a diode directly, and you're watching the output of the diode, maybe with a voltmeter, maybe with something more fancy. But the bottom line is you're seeing an electrical signal come out of the thing as a result of the optical signal coming in. A simple way that you could build a real system in that regard is you could put a chopper on the source end, basically turn the laser on and off, okay, maybe at 1,000 hertz, okay? And now, if you put an audio amplifier on the diode that is at the focus of that lens you're using for receive, you're going to hear a tone. Or at least if you put an amplifier there, then you might hear the tone. And lo and behold, you have a real optical communication system with electrical transmitting and electrical receiving. It's a real, honest to God, electromagnetic link in all respects. And by the way, it counts for grid squares if you're interested in doing that kind of thing for microwave credit. It is, in fact, electrical detection and electrical modulation, so you're good. Anyway, so even the simplest kinds of systems are manageable and understandable, okay? Now, if we convert a signal to a lower frequency for more processing, we call that a superheterodyne receiver. And heterodyne is the process of converting a signal to different frequencies, whether it is upward or down. And then another way that you can build a signal receiver is to digitize the signal at the original frequency directly. Eisen can tell us a little bit about that. Whether it was truly directly or just one step removed is another question, but it can be done directly if your digitizer is indeed faster. And there are some ways to extend the range of a digitizer, but we won't go into them now. This digitizing directly at the frequency of interest is becoming more and more common as the parts that we have are getting better and better. So signal source, direct generation of transmit frequency, for example, a laser diode or a power LED, which if it's monochromatic or close to it, you can actually use it for credit for doing, the VUCC stuff. Modulation of the laser diode might be challenging. It depends on exactly how you're expecting to do it. But bottom line is it's really easy to turn it on and off, so that's one way to do it. Frequency of the laser, or wavelength, as people talk about it in that domain, the wavelength is limited by the device, by the attributes of the device itself. It's not likely you're going to make large changes in wavelength with a laser transmitter. It's going to do what it wants to do, and that's about it. Another alternative, much, much lower in frequency in the microwave region, is a gun diode cavity oscillator. And we have one of those buried somewhere around here. Oh, here it is. Not buried at all. This piece right here is a 22 gigahertz transmitter. There's the gun diode inside of a little chunk of waveguide at the back end of this thing. And that goes out through a little piece of waveguide to the front. And that's a retro Yagi, if you want to call it that. It's two elements. And that spurts the signal back at the dish. Lo and behold, we make 22 gigahertz here. It comes out here, bounces off the front of this, and then illuminates the dish. And you have a very simple but effective transmitter. And typically, this kind of thing might be used for moving data signals at a few megabits per second from one building to the next to the next in a campus, like at school or in a large business. But that's actually a real honest-to-God commercial device that you see there. We could use that device on 24 gigahertz if we changed the gun oscillator. Or, with some luck, you might be able to tune that beast from 22 gigahertz to 24 gigahertz, but it's probably unlikely. So anyway, that's an interesting example of a very simple way of building a microwave, conventional microwave in the gigahertz region, not a light thing, and yet it uses direct generation right at the frequency where you want to transmit. No fiddling around, there it is. Surplus equipment like that is not particularly hard to find. You go to a major ham fest, you're probably going to find a couple of those or something like that floating around. That one came from a ham fest in southern New Hampshire, which I'm going to tomorrow.
I was gonna say, this week, it must have been out
Near
there
fest.
already.
Near fest.
Near fest.
I won't be there, but I do have grading responsibilities.
Oh, well, the fall version's a little better.
Yeah.
Yeah, and this one got messed up because the weekend wasn't reserved early enough. So it's offset by one day early, but at least it's still going. So another place where you can find commercial equipment for the microwave band is, for example, especially if you want to do direct radiation or direct generation, police radars. They're a wonderful source for gun oscillators. And in the radar, they do nothing special. They just sit there as a source that's just on all the time. And that signal is transmitted through their little horn out into the world. And if it bounces off something that's moving, the signal comes back as Doppler shifted. It mixes with the outgoing signal in a diode that's in the waveguide. And lo and behold, you get an audio tone that's related to the speed of the object. Okay, so bottom line is, for these kinds of things, the stability is only fair. You might be able to use it to transmit wideband FM, for example, and at 10 or 24 gigahertz. And the wideband FM occupies about 200 kilohertz of bandwidth, 75 kilohertz deviation. We use the same deviation standard as broadcast FM transmitters do. Why? Because then your IF receiver can be very simple, because there's hardware that you can use to receive that kind of thing. Okay. So that's nice. You can make a signal and radiate it directly, but for most things, you really want to start out at a lower frequency and then move it up somehow. The simplest way is to start with a really stable crystal of one sort or another, or a synthesizer at a moderate frequency, between 10 and 100 megahertz or something like that, and then multiply it. And multipliers are basically, you take some kind of a nonlinear device, diodes certainly work, and another option is to take a transistor amplifier and overdrive it. Just push much more signal into it than it would normally get, and it will distort. And so now, coming out of the output end will not be a sine wave, but rather pulses that are related to the drive frequency. Those pulses have harmonic content. How much depends on the details of exactly how you use the device, how you bias it, and all that good stuff. But suffice to say, it's pretty darned easy to get a transistor to give you a lot of second harmonic and third harmonic, and maybe even fourth harmonic. Lo and behold, if you do this and repeat it, if you repeat the process, you might take a, I don't know, pick a number, a 12 megahertz oscillator, stuff it into a nonlinear amplifier because you're driving it too hard, you might get 48 megahertz out of it. Take the 48 and run it into another amplifier, and you might get 3 times that, and so on, until you get to the frequency that you want. And you will put filters in between each of these multiplier stages. And there's some good technical reasons to do that, because you don't want those lower frequency ears, if you will, sneaking in to the spectrum of the output. You want just the final frequency and nothing else. So if you put filters between the stages, that prevents the lower frequencies from leaking into the final signal that you're generating. Okay, so you can get up to the desired frequency in one way or another. How good can this be? Actually, pretty darn good. This was the go-to method for generating all kinds of signals. For example, in two-way radios before the beginning of this century, most equipment didn't use synthesizers, or if they did, they were low-frequency synthesizers. And then they went to this process, multiplying the signal to get up to where they want to go. So let's, for example, take old two-way radio equipment and that could generate signals up to 900 megahertz. Okay, that's not really in the microwave region, but now you can take that 900 megahertz or something nearby, like maybe 1,000 or whatever, and multiply it in the microwave range by 2, 3, 5, some moderate number, and you quickly get up into the microwave frequency. So then you can apply the signal to a microwave frequency multiplier using the same general idea and get to what final signal you want. Now, that said, let's see, do I have something like that here? Maybe. I'm not sure if I do. I might not have brought. Yeah. But I have pictures. That's a picture of a two-way radio circuit board that was taken out of an 800 megahertz two-way radio. And lo and behold, the crystal for that is hiding, if I can, there it is, lower left, kind of under the lip. Can you see my little marker? You see a little piece of foam plastic there, but underneath that piece of foam plastic, there is a module that is the crystal oscillator at 16 megahertz in this case, or maybe 18, I'm not sure which. Okay, so it goes through several sections of multiplication using transistors to get up to 800 megahertz, or at least it used to. I wanted 1152 megahertz, so I took the last stage, and instead of making use of the last stage as it was, I changed the resonator on the final stage, which is up in here, if you can see my marker. You get it? See it? That pair of filters was handmade in order to resonate at 1152 megahertz instead of the original 800 megahertz or thereabouts. And so the order of multiplication in the final stage was larger by one factor. I think instead of a ×3, it was a ×4 when I get done, or maybe it was a ×2 and now is a ×3. I don't remember. I'd have to go back and look at things. And then after we've made the signal at 1152 megahertz, lo and behold, we go through an amplifier in the back here to raise it to about 1/4 watt at the output. And we were then able to use that 1/4 watt and go into various microwave multipliers to get up to microwave frequencies at 2 gigahertz, at 3 gigahertz, at 5 gigahertz. So the bottom line is this is a signal source at some relatively high, but not final frequency. And I used it to make signals at a bunch of different ham bands. And it just turns out, by luck, that the ham bands at 2 gigahertz, 3 gigahertz, and 5 gigahertz are harmonically related. And so if you have a single source at 1152, by just changing the multiplier, you can in fact get signals at 3 or 4 different microwave bands and still use only one source. So that's kind of cool. Yes?
Question on stability. Let's say if you have a, let's say a clock that's running on 1 gigahertz, that's 1 parts per million.
Yeah.
Um,
That's
but-
nowhere near good enough.
Probably not good enough, but I'm just giving an example. When you double it, would it increase to 2 parts per million?
No,
Still 1 part.
it's 1 part per million, but remember, the million has gone up.
Yeah.
So
Okay.
the signal frequency goes up as well as the amount of fluctuation.
I see.
So the part per million remains the same, but the absolute frequency is double the variation.
I see.
So something 1 part per million at 1 gigahertz is still 1 part per million at 2, but you get the idea. Instead of 1,000 hertz error, it's 2,000 hertz. So how good can this be by just this surplus crap? You know, gee, it's a 16 megahertz crystal. It's sitting down there and going at very low frequencies compared to the output. Well, see that knob at the far left corner? Down here, that little black knob? That controls a voltage that goes into the crystal oscillator that is normally used to compensate for temperature variations. In this case, I've co-opted that control line and instead used it for manual frequency control so that I could move the microwave frequencies at 2 gigahertz and higher around by a few kilohertz back and forth. So essentially I had a fine tuning control for this whole thing. And so lo and behold, yes, I could actually set this frequency accurately with the little knob there if I knew when I was there. That's another problem. Are the crystals good enough for this? And the answer is yes, they were, but they did have to have a tuning range of about 10 parts per million to move it around somewhere within that range. But with a 10-turn pot on that front panel, that was no problem tuning. You go, no problem at all figuring it out. That, oh yeah, here he is, this is his seat. Okay. So the bottom line is, yes, you can start with a very low frequency crystal oscillator, multiply the heck out of it, and have a useful transmitted signal on the far end. And over short terms, this is quite stable enough. Once you tune in, you don't have to sweat it. It's not going to move for the next 5 or 10 minutes. It's going to stay within a few hundred hertz, even at 5 gigahertz. So how did we get to 2 gigahertz? There's the example. If you see this little beast, if we look in the upper right corner of the right-hand box there, there's a little black pill. You see that? I'm going to try to find there it is again. Little black pill right there. And the input is here at the far left. Signal comes into the little black pill. And that's the overdriven amplifier. That's a little microwave transistor capable of about 300 milliwatts or more. And you drive the living daylights out of it at the input at 1152, and all kinds of things would come out of it. But on the far right of this thing, we see that there's a piece of transmission line, a little piece of copper sheet, which is spaced about 1/10 of an inch off the bottom. And it's a half wave long at, would you believe, 2304 megahertz. And you adjust that by, if you look at the middle of that little thing, I can't get this darn thing to, there it is. All right, right in the middle of that thing, there is a little piece of copper standing upright vertically there. And then if you look to the right, see there's a little piece of copper, thin copper flashing that you can sit there and move back and forth. So when we make these things, okay, let's tune it up. You can tweak these trimmers. There's one here at the input, there's one here, there's another one there, and then we have a little capacitive wave in the air capacitor, and just push it around with an insulated tool until the maximum is seen, and you say, okay, I have a doubler. For about 200 milliwatts in, this produced at 1152 megahertz. This produced about 250 to 300 milliwatts at 2304. Success. That's not a trivial amount of signal. That will go many tens of miles. In fact, on a line of sight side, if it was a truly line of sight thing, it'll take you out to whatever line of sight location you can find, because you're limited to how high a mountain you might have. And here in the Northeast, that's about 6,000 feet. So the bottom line is, okay, if there is a mountain 6,000 feet high and I'm at another mountain, say like Mount Greylock, 3,500 feet high, okay, what's the greatest distance I could possibly talk and still be line of sight? And the answer is in the 100-mile plus range, maybe 100, 130, somewhere around in there, before you bump in to the Earth curvature.
Because my setup, the output will be around 100 milliwatt and work over 100 miles. So my setup was 100 milliwatts.
Okay.
Will work over 100 miles.
Yeah, right. So, proof.
It's weak, but
No matter how you get the 100 milliwatts or 250 milliwatts, this works. Hisense Way is much more modern and in many ways much better. In any case, you can use junk, spare PC board, just use a shear, cut it up into the pieces you want. It's amazing what you can build that actually works. Here's the 3 gigahertz version of the same thing. Same drive at 1152 megahertz times 3, lo and behold, produces about 100 milliwatts with a quarter of a watt of drive. That's still plenty to go a long ways. 5 gigahertz, anyone? Well, the 5 gigahertz system actually was integrated a little bit more than 2 and 3 gig system. You didn't see any antennas in those previous 2 things. But on this one, guess what? This is the entire modules with 5 gigahertz, and it uses a horn antenna. This horn antenna on 5 gigahertz has about 20 dB of gain. So it's not trivial. What is it for a horn? Just a simple, ordinary, go to the hardware store, tin horn. Works just great. It doesn't have to be smooth. It doesn't matter. It has to be something that's reasonably smooth with regard to the wavelength. The wavelength here at 5 gigahertz is 6 centimeters. That's pretty good size. So small ripples have absolutely no effect on it at all. So the multiplier in this case is a salvaged module from some commercial microwave gear. And it is a high order multiplier that is roughly times 5. Well, it is times 5 from 1152 to 5760. And we salvaged that out of some commercial gear. And we were able to find enough of them to satisfy our needs. Surplus is great. And from there, it goes to a circulator, which then feeds a horn. Received signal comes back in the horn, goes through the circulator down to the mixer. And a little bit of the transmitted signal, you see that little screw sticking into the side of the waveguide, the circular guide? You see that? That's a spoiler. That's a VSWR spoiler. It's purposely put there to reflect a little bit of the transmitted signal back down toward the equipment. And that provides the local oscillator signal for the mixer. So, okay, I'm transmitting, but I'm also making local oscillator for my receiver. How does that work? That works just fine, as long as the other station is offset from my station by the intermediate frequency that I have in my receiver. So let's assume for a moment that the difference is 5 megahertz. The equipment doesn't know the difference between 5760 and 5765 megahertz. It could care less. It's going to transmit that either one without any concern. So a little bit of 5760 comes in. Other station knows enough to transmit on 5765. You get a beat note between the two, 5 megahertz. It's down in the region where you can use a lot of different kinds of receivers. HF receiver will do that just fine. Lo and behold, you got a 5 gigahertz system. It's very, very simple. So you can build simple stuff that actually works. So signal sources, direct synthesis, sure. We need high frequency microwave source somehow, no matter what the configuration of the system, whether it's these simple things that we're using for examples at this point, or whether it's a full-fledged converter receiver that people call transverters. But the bottom line is, you can buy good synthesizers or you can buy bad synthesizers. A friend of mine recently bought some out of China that were not very well engineered. And it turns out that they used the same regulator for the VCO as they used for other things in the synthesizer. And when these other things drew just a tiny little bit more current on and off as they did their thing, it produced noise in the phase lock loop, and it made for a messy signal. So the bottom line is, just because it's there doesn't mean it's good. So by all means, ask people who have tested, make sure you look online, and if somebody else has posted something that said, oh, this particular model, it's got a bit of an issue. In that particular case, if you go in and you change the way the regulators work, lo and behold, maybe add one, all of a sudden you can fix the problem. But the point is, buyer beware. Signal sources, frequency mixers. The vast majority of microwave equipment uses mixers to change frequencies in one way or another. Combine a local oscillator signal with a communication signal to move the frequency up or down. It's a mixer. That's what they do. Frequency multiplication function is what a mixer really does. You take signal A, different frequency than signal B, put it into a nonlinearity we call a mixer. Sometimes we put it into a nonlinearity which we call an amplifier. That's a mistake. Oops. But that happens. Okay, so we do that, and if you do the arithmetic, guess what? You get the two original signals, you get the sum, you get the difference between those signals. Lo and behold, you can use this process to either move a signal up or move it down. And then you use filters to select the desired result. If you're moving it up, obviously, you use a filter on the way up. If you use it on the way down, you use a filter before the object, before the mixer, to limit what can get into the mixer so you don't hear things you don't want to hear. Okay. So this collection, local oscillator, mixers, synthesizers, whatever, if they have mixers for moving signals up or down, we call it a converter. If it's a receiver, we call it a down converter usually because microwave signals are high on frequency. For transmitter, it's an up converter. Work both ways. Box that does both is called a transverter. You can go buy transverters, all kinds of different transverters for the microwave bands, or even for the VHF bands if you have an HF radio. It's a very common term. What are some mixer types? Well, the simplest thing is you take a diode and you grab a piece of waveguide. Oh dear, I don't actually have a waveguide mixer here, but here's a piece of waveguide. We drill a hole in it somewhere before the end of it. Let's assume this is the end. And if you put the hole about a quarter wavelength away from the shorted end, what's going to be the situation? the voltage or the E field inside the waveguide is going to be largest when it's a quarter wave away from a short. And lo and behold, that's where you put your diode. Simple as, oh, here we have two diodes in a mixer configuration. This is a balanced mixer. And you can kind of see, kind of bad light here, but you can kind of see there are two waveguides here beside one another. And there are places for two diodes to be acting as mixers here. This is actually a balanced mixer because of the hybrid that is here. This is an example of just putting a mixer, or a diode rather, into a waveguide and positioning it properly. Lo and behold, it mixes. The IF will come off on the lead of the diode. You need to bypass it for the microwave frequencies. Okay, so a simple diode or a diode in a waveguide is a mixer. Trouble is that it has a lot of junk coming out beside what you want. Because the original two signals, it's got the sum, it's got the difference, and probably a whole bunch of other things too. Well, okay, what are some things that we can do universal? Well, we can use what's called a single balanced mixer with two diodes in an appropriate place. And you can make it so that the local oscillator is balanced at the output of the mixer. And so lo and behold, the one is 180 degrees different from the other, and you end up with little or no local oscillator leakage. This is a good thing. The same thing applies to a double balanced mixer. Well, now you balance both the local oscillator and the original RF frequency, and you get neither of those. Well, that's not really true. You push them down by maybe, if you're lucky, 30 dB. At very low frequencies, you might even get 40 dB of cancellation of the things you don't want. But you're never going to get huge numbers. By that I mean, you're never going to get like 50, 60, 70 dB of cancellation, unless you sit there and you tweak it just right, in which case it won't stay there. So forget that. Bottom line is, you can use balanced mixers, and that's very, very common. We'll see one in an image here in a bit. All right. Image reject or image recovery mixers are yet another wrinkle in the game. It actually decreases the image response, and it makes the desired signal a bit stronger, maybe, if everything goes well. Usually these consist of two mixers that are combined in such a way that you can actually recover some of the energy that is otherwise lost. Bottom line is, they're much more expensive and probably not worth the effort. And then there are active mixers. I just put these down there because some mixing schemes actually use transistors or switches where the diodes would normally be. And it's called a sampling mixer, or you can call it an active mixer if you want. I don't care. Bottom line is, anytime you sample a signal by any means at all, you are creating the same kind of thing as multiplication of those two signals.
Question.
Yes.
How does a diode actually do the mixing? Because I know people using transistors to mix, but how a diode?
The diode, if as long as a rudimentary thing, you don't have to depend on the diode characteristic curve at all. As long as you turn it on and turn it off, that's all that matters. Surprisingly.
But how does it do mixing? Let's say,
Excuse me?
how does it do mixing? You will have a local oscillator input, you will also have
Go ahead.
input. Where's the circuit?
A sampling of a signal is the same as the multiplication of that signal with the other signal.
Okay,
Mathematically identical.
I see. I see.
That might turn you on, having some mathematics background.
Yes, in the DSP, I think that's in the very first lecture, how to do samplings, but,
Yeah.
yeah.
Turns out a sampler is a mixer, whether you want it to be or not. Sometimes you don't. Okay, so sometimes the diodes have very smooth characteristics, sometimes they don't, but in reality, they don't have to. It's more important to have good balance between diodes in a balanced mixer so that you get the first 20 or so dB for free of preventing the stuff you don't want. So this is an example of a surface mount mixer, which is commonly used in an inexpensive, I don't know if I've got an open one here or not. I don't think, wait a minute. Yes, I do. This has a mixer, I'll pass this around here, which is sitting right next to this connector here. Connector is on the end plate, so that's how you can find it. And it's a little ceramic thingy. Shoot. Pass it, and then over there.
Technology sat on one side of the room.
Just a little white thing.
Yep. Cool.
So frequency mixers are a wonderful idea. They are tons and tons of things. There's so many out there in the world, it's not even funny. They're used in almost every kind of radio system you're going to meet. But they come with baggage, and that is, they all come with unwanted output signals or sensitivity to unwanted receive signals. And so filters are needed no matter what. Now, they may be more or less needed depending on what other techniques you might use. Filters you use to keep the size of the unwanted signals down. Keep in mind, no matter what kind of thing you're making, communication systems deal with absolutely huge dynamic ranges. Think about a transmitter at 100 watts and a receiver with a bandwidth of, I don't know, pick a number, 1 kilohertz, and a noise figure of, pick a number, 3 dB. You're looking at a dynamic range of over 200 dB.
In theory, right? In
No,
practice.
in reality. In other words, the transmitted signal is that much larger than the received signal that could be received at the other end. And once you go over the horizon, oh my gosh, you can still hear it.
Yeah.
In any case, whatever the number is, and I didn't actually run through the calculations, bottom line is it's a very large number. It's well over 150 dB. It depends on how much transmit power you have and what bandwidth you use and all that good stuff. But the bottom line is no amount of cancellation will solve that problem. However, we can use filters. And they come in all shapes and sizes, and I brought a ton of them today. First of all, there's the coaxial resonator. And let's see, this is probably the best way to explain it. See all these little pipe caps in this thing? Form. Lo and behold, those are filters.
Adjustable filters.
4 filters in there. Each one just one pole, but they are filters. So that's one of the simpler types. Then there's a whole laundry list of various other types, which we'll touch on a little bit. They can be very difficult to tune, but design programs are available for free at low cost, if you know where to look for them. If you are interested in doing some work like that, I can help you get started. Network analyzers help, but you don't have to have them. I have demonstrated techniques for tuning filters that I looked up that were published in the 1950s when nobody had spectrum analyzers. And so the engineers were scratching their head trying to figure out how the heck do we actually do this? That's the same thing as a spectrum analyzer. I'm sorry. I can do it with a diode detector and a DC amplifier that feeds a meter and nothing else other than a signal source. That's all you need. And you're not just looking for peaks. But that's a whole nother presentation. And it is absolutely amazing what you can do. Anyway, you can do it manually with a signal generator and a sensitive detector. And I wrote a paper on that. It's a very long one. Anyway.
Should we make that as part 3 of the?
It's so specialized that unless you want to actually learn how to do filters, it's a bit much.
Okay. But I was interesting.
But it is fun to actually sit down in front of a spectrum analyzer or a network analyzer and tune it up the old-fashioned way, and then move it over to the high-tech stuff, and holy crap, it's tuned exactly right. The answer is the theory that the old method is based on is entirely consistent with the mathematics, so be happy. It works. Anyway, what I just passed around is the same thing that you see here. Yep. And what's in each of those pipe caps is a simple coaxial structure. The center conductor of the coaxial structure is the screw. The outside is the pipe cap. And then there are some little probes that stick in the bottom, which you can't see because they're all covered up by the pipe cap. And if you look carefully, you might be able to see where the probes come off of the microstrip lines and go into the cavity down below. In this particular figure, those probes are larger than they really are in real life. They're somewhat smaller than that. You can adjust the probe length to adjust how much coupling there is through the filter. The coupling is high, the loss is high, but it's narrow. And if the coupling I'm sorry, let's try that again. If the probes are high, the coupling is high and the loss is low, but it's wide. Okay, and then the converse is true. If the probes are short, the loss is high, the frequency selectivity is very sharp, so you're trading back and forth between those things. Okay, now for some real filters. This is comb line type. What's a comb? Have you seen a comb lately? Sure you have. You probably comb your hair every once in a while. Some of you probably not. What's a comb? Something like this, right? A whole bunch of fingers. And they're all in the same direction. That's a comb line filter. In this particular case, there are 6 elements inside of this box. And they're all in the same direction. That's one way. Here is another comb line filter. This is the one that we actually use on 2304 in the new Rover that's sitting in that suitcase over there. It's a 3-element filter that used to be on 225 megahertz that we've moved to 2304. It used to live in a radar that had 64 channels. A lot of nice hardware in a 64 channel radar.
Yeah.
Very nice. The boss said, we gotta get that damn trailer out of here. Fry, go with your buddy Gene and take it apart. Make it go away.
Okay.
Okay. We got 64 channels of radar hardware out of the game. Some was not useful, but an awful lot of it was. But by the way, the low noise amplifier for the radar actually worked pretty reasonably as a low noise amplifier at 5760 megahertz. So, okay, boss, we'll make it go away. Thank you. Other filters. Here's the top one is an interdigital filter. Used to be on 3.7 gigahertz. 3.7 to 4.2 gigahertz is a section that has been used for both satellite communications and point-to-point microwave links on the Earth. They don't use it for that much anymore, but if you find some old hardware that used to be used for that, lo and behold, the filters in there are real handy for the 3.4 gigahertz handband. Ta-da, whoopee. And then down below, sometimes you get just plain dumb lucky. The post filter that you see down there is actually a duplexer with one channel for the receiver and a different channel, or a different frequency channel for the transmitter. But, well, you know, we only need one. So lo and behold, this one happens to pass the 5.76 gigahertz signal that hams usually use without any retuning. Yippee! When I figured that out, I looked at that and I said, okay, how many do you have? He said, oh, I got about 20. I said, what's a good price for all 20? I ended up walking out less than $10 a piece.
Jeez.
But we have a very nice ample stock of filters for 5.7 gigahertz now. Okay, so what about another physical form? Those were all air filters that would just look like the dielectric was air. Here's something that fits on a circuit board dead flat down on the board. It's all a matter of the lengths. You can build filters this way, but they're usually much more lossy than what you would get if you built them with just air as a dielectric. But this has the advantage that lo and behold, once you print the pattern correctly, you're done. That's the end of it. Doing the design can be a little challenging though, because among other things, you have to be able to compensate for changes in the dielectric constant of the circuit board that you're going to use. This generally means that you need to make the filter a little bit wider than you'd like to. And you need to do that because you never know what the next batch of circuit board is going to look like unless you buy a very expensive board that is meant for building microwave filters right from the go. And yes, you can buy that stuff, but it's about 10 times as expensive as ordinary board is. It's Teflon. The thickness is very carefully controlled. The dielectric constant is very carefully controlled. It's meant for the job. But if you're willing to accept, this filter didn't come out quite right, you can get away with using relatively simple filters this way. This is 1, 2, 3 elements only, and that's not too bad to do in this format. You can use more, but it can be a little challenging. I have an example over here of a large number of sections. Okay, well, actually, that's not true. Here's an example of a 3.4 gigahertz 3.4 gigahertz transverter that uses 2 3-element filters on transmit and 1 3-element filter on receive. And in this particular case, the board stock is actually RT Duroid, which is a Teflon board. Teflon and fiberglass mix that pass this around. be gentle with the connectors and just don't manhandle it, because you can flex that board very easily. If you want to, you can bend it. Not good. But those are little 3-element filters mixed in. Amplifiers. Oh my. Everything comes in amplifiers. All kinds of amplifiers. Little, big, even huge. All right. Here's a medium size. This is like in the tens of watts is probably reasonable to talk about. The devices themselves in that amplifier that's on the screen right now, the devices themselves are 125 watt devices. So you might ask, why in the world are they using 125 watt devices, and 2 of them no less, in order to produce 50 watts, which is what this thing was intended to deliver? The answer is they wanted very low distortion for the kind of signal they were transmitting, because of the modulation that they chose. So lo and behold, this has got a lot of hardware in order to do only a little bit of power. Luckily, as hams, we're not limited by that same distortion limitation, because we're not using highly sensitive modulation techniques. So we were given 1,000 of these. The Mount Greylock crew were given 2 pallets this high, stacked with these.
Are they now in the resting channel?
We're now down to about 150.
Okay.
And nobody's buying them from us anymore, because everybody who even dreamed of maybe wanting one has one. And have done nothing with it. So, this is the palette inside. The top 2 layers of this, the very top layer has a microprocessor in it. Yay. The middle layer has power supply circuitry in it. And the bottom layer is the only one that's silver plated. And is this layer is the only one we care about, because we don't need the fancy power supply, and we don't need a microprocessor because we're not going to do fancy things with it. And what we do want out of this puppy are these 2 transistors. Each one is capable of producing 75 watts at 2304. Now, generally, for a lot of weird reasons, we don't try to use both of the transistors. One reason was that the elements on either side of the transistors that split the signal, they're called hybrids. They then go through the 2 transistors, and then the signals combine again in these hybrids. The hybrids are not made for 2300 megahertz where we are. They were made for 1900 megahertz, and they don't work very well at 2300. So lo and behold, the splitters and combiners in that network, no good. But it's still, one transistor still does 75 watts, which is not to sneeze at 2304. You can almost cook hot dogs with that. Microwave oven, normal frequency, anybody know?
2.4.
Keep going.
I don't know.
2.45. 2450. Ham radio frequency band, 2300 to 2310. Then there's nothing. Then 2390 to 2450.
Okay,
The
so
microwave frequency is in the ham band, or right at the edge.
so you can actually tune it a little bit to make it actually a microwave
You
transmitter.
probably could use a microwave oven as a ham transmitter.
And the cook hot dogs.
CW, yeah.
Just make sure you don't cook yourself.
Yeah, point it the other way.
Yeah.
Open the door,
Yeah.
stand behind it, not beside it.
Correct.
I mean, hey, there was a microwave in the tech dumps the other day.
I'm gonna go and take my microwave apart.
Please, please, if you're gonna do that for real,
No.
come talk to me. I'll tell you how you can safely do it.
Exactly.
Oh, there is another YouTube video I recently watched like they are using battery to power a magnetron. I believe that's the part that's producing the RF in the microwave oven.
They're using a battery to do what?
To power the magnetron, or that's the parts, the RF part in the microwave oven, right?
Yes, but how did they get the high voltage necessary?
ZVS or something.
Or what?
ZVS. I can probably send you the link to the video, but it's
Okay.
just shown that it is possible to operate with
Oh, yeah,
battery,
you can do
but
all
at
kinds of
very
things.
low wattage,
Um,
not like 1500 watts. you know.
no, but the problem is the magnetron is essentially an oscillator. If the frequency, if the operating voltages are changed, it will no longer oscillate at the right frequency. And we can go to talk about exactly how that works offline. The electrons that are radiated off the cathode go in a curlicue pattern around the periphery of the magnetron. And the problem is, if you change the voltage on the anode of that magnetron, those electrons no longer properly go in those orbits. So it might work somewhere maybe, but it's certainly not going to work anywhere near the way it originally was intended to. On the other hand, there are some people who have actually done some calculations, and you can use a magnetron as a injection locked amplifier. By that, I mean, if you stick a signal into the magnetron at a frequency very close to where it wants to oscillate, it will then oscillate at the frequency that you're sticking into it. So you can get an output signal that's 10 times, maybe even as much as 100 times stronger than your locking signal. And so, okay, now I have a 1,000-watt transmitter, but I have to put information on it somehow. And one way is, I suppose, if it moves around in frequency quickly enough so that you can agilely move the frequency here, there, and everywhere, and the generated signal is clean enough, which is highly doubtful, you might be able to make a real communication system device out of it. I know people have run through the numbers, and yes, this can be done, but it's kind of at the limit of what is possible. But watch your ass, because the larger microwave ovens are more than a few hundred watts. This is serious power, and you can get damaged. By the way, a couple of months ago, I was visiting my brother, and I opened up his microwave oven to heat up some coffee, and I was looking at the microwave oven, and I noticed that the box had rusted. Right near the door, there was a slot about that long and about a quarter an inch wide, where the bottom piece of the interior box joined the front piece of the interior box and the door seal and all that stuff. Okay. What's the wavelength at 13 centimeters?
Well, good for that.
Well, the half wave is what counts. Because if there's a half wave slot, you have a radiator. A very efficient radiator. So at about 3 inches, yeah, you got a leak. You got a big leak. So I said to my brother, Walter, do not turn this thing on ever again. Unplug it now and scrap it. He gave it to me. So what's it useful for? The power supply, maybe,
Yeah.
Transform.
Transformer, maybe.
and the actual magnetron, maybe. I already got a bunch of magnetrons that I could use, so it's not that hard to find them. Anyway, bottom line is, watch your ass if you want to play games with a magnetron. It is basically an oscillator. It does not really function as an amplifier, so it's not easily adapted to a communication system.
Grade 10, real quick though.
Get something right. Okay, so anyway, this is a picture of what you just saw. And there's the palette. Did that thing get passed around?
Take that microwave, put it up on the telescope, we'll send that up in the air.
Yeah, right?
Over on it.
Sometimes these are actually attached to the back of the dish, or it's self-integrated because the system isn't that big, so that you will have lower loss and have your high-end radio.
Yep, that's it.
This is not converted. This is as it originally was. Type in.
I know. Well, it's a joke, what, our repeater guy,
Yeah.
every radio he owns has end connectors in the back of it. He will not do anything other than end connectors. I tried to get him as a joke, build me a piece of hard line with 259s. He looked at me like I was an idiot.
So here's the question. Good question.
Yep.
What is a good reason for for using a type in?
Give him a much higher frequency.
Okay,
With
that's
a
one.
lot less loss.
That's sort of the same answer.
Yeah, okay, yeah, you're right.
Anything else?
Not sure.
Think about it. What's it look like? How does a type N look different? Water sealed.
Yes,
Type N connector properly installed is watertight.
or all 259s that we install with HF stuff, we have to seal up with.
You always have to find a way to seal it up.
Correct,
Not only that, but once you make it, that part also needs to be sealed.
correct.
And so that's a pretty bad downside. And so if I were doing anything outside where I could not protect it otherwise,
And
I'd use a type N no matter what the frequency. On the other hand, in terms of RF, up through 250 megahertz, UHFs or PL259s, whatever you want to call them, are perfectly adequate. I usually stop at 2 meters. I'll go as high as 2 meters with a PL259, but not beyond.
I mean, I've got on the 440 stuff on the truck, but that's,
Yeah.
yeah, I'm not using it often and
And if it's inside, it's kind of like, it's not right, but it's okay. We'll get away with it. All right, so there are two MRF-125 transistors on this thing. Even one of the devices makes 75 watts all by itself. So what do we do with the other one? Well, we've already said that the hybrids in and out don't work. So it turns out that on the left of this picture, you see another square here that has an Ericsson label on it. That's the driver module to the big transistors. And it raises the signal power from about the 1 watt level or the half watt level up to the drive level for the two big transistors. Unfortunately, it has negative gain on the frequency that we want, 2304, so it's useless, and it's matched internally between stages, which makes it even more useless, because you can't even get at it to change the matching. So the bottom line is the Ericsson module is useless, so we use one big transistor to drive the other big transistor, and we end up then with a pallet that will give us 75 watts from a milliwatt or less. So that ain't half bad. Special since it's free.
freeze the golden word.
Another example of what you can find, this I found on eBay from Israel. They were tearing out some WiMAX systems. Basically, Wi-Fi systems on steroids with some significant power to serve communities rather than just a single household. And these worked at 3.5 megahertz, 3.5 gigahertz. And as I received them, they essentially work as is on 3400. So, ta-da! Not only that, but they come with an LNA inside, part and parcel of this front-end module. They're calling it FEMs for short. So this thing sits up by their dish, I guess. I've never seen the whole thing. This FEM sits up in the dish. It's connected to the inside unit downstairs. It has a bunch of control connectors. As you can see on the right, there's about a 20-pin control cable. And the thing down below it is of power. And that assembly will do less than 1 dB for receive noise figure and delivers 15 watts output. I ended up having to spend about, well, the first ones that I bought, I had to spend about 50 bucks for, and then I managed to get the remainder in the $20 to $30 range, depending how many I bought for me and my friends. So I ended up, I think, moving about 50 of these into the ham radio community. This is what it looks like inside. Most of them were very clean, just like that, because the outdoor, the rubber seals around the periphery were all intact. And no matter what the outside looked like, the inside was always pristine, just like this. So where can you find equipment for whatever you're doing? Almost anywhere. Microwave antennas. Okay, we have a few here. The smallest that's practical is probably a dipole. And in a rather queer sort of way, let's see, is there anything else worthwhile here? No. Let's turn on the lights.